Today, we're diving into something truly revolutionary. It's a kind of technology that's designed not just to be used by the human body, but to actually merge with it. Welcome to the world of stretchable bioelectronics.
So it all starts with a really simple but powerful question that drives this entire field of science. Our phones, our computers, they're amazing, but they're also super rigid and fragile. So it makes you wonder, why can't our electronics be more like us? Soft, flexible, and always in motion.
And when you ask that question, you immediately run into this huge fundamental problem. On one side, you have our electronics. They're stiff, they're brittle, they're flat. And on the other side, you have us, our bodies. We're soft, we're curved, and we're constantly moving. By their very nature, they're just completely mismatched. And what's wild is just how massive that mismatch really is. I mean, take a look at this chart. It shows stiffness. See silicon over there? The heart of all our gadgets? It's at 130 times gigapascals. Now look way down at our softest tissues, like our brain. That's measured in kilopascals. We're talking a difference of millions of times. It's an absolutely epic mechanical divide.
To really get a feel for what this means in the real world, our source material gives us this fantastic analogy. Trying to put that old, rigid tech into our soft, squishy bodies, well, it's basically like
trying to wrap a piece of glass around a balloon. You can just picture it, right? It's an impossible task. No matter what you do, either the glass is going to shatter or the balloon is going to pop. There's just no way those two can coexist peacefully.
And inside our bodies, that pop is what's called the foreign body response. The body basically freaks out. It sees that stiff implant as a threat. It gets irritated, it gets inflamed, and over time, the body literally builds a wall of dense scar tissue around the device, what's known as a glial scar. And that wall, it basically suffocates the electronics until the signal just fades away and the device fails.
Okay, so that's a huge problem, right? You can't just force stiff tech into a soft body and expect it to work. It's a massive engineering and biological challenge. So the big question is, how do we solve this?
Well, the answer isn't to try harder with the same old stuff. The solution requires a complete shift in thinking. Instead of forcing that glass onto the balloon, you have to invent something totally new. It's like building
circuits on a rubber band. And that right there just perfectly nails the new approach. Just imagine an electronic circuit that can stretch and twist and bend right along with that balloon, or in our case, your skin, your heart, or your brain, without breaking and without causing any harm. That is the core idea of stretchable bioelectronics. So how on earth do you actually build a circuit on a rubber band? It sounds totally sci-fi, I know, but it really boils down to three key engineering breakthroughs. Let's call them the three secret ingredients.
Okay, so here they are. It starts with a soft, squishy foundation. Then you've got to have wires that can stretch without snapping. And finally, you need a really clever way to power the whole thing without a big, rigid battery getting in the way.
So that first ingredient, the foundation, that's actually the easy part, believe it or not. Instead of using those stiff silicon wafers, scientists use these soft, rubber-like polymers called elastomers. A really common one is PDMS. It's flexible, it's transparent, and it's thousands and thousands of times softer than silicon, which makes it a much better match for our bodies. Now, this is where it gets really clever. The wires. You basically have two main options here. First, you can use materials that are just naturally stretchy and conductive, things like liquid metals or special gels. Or, and this is my favorite, you can take a rigid material like gold and just shape it in a really smart way that allows it to stretch. The best analogy? Think of an old coiled telephone cord. The wire itself doesn't actually stretch, but that springy, coiled shape lets it extend and retract without ever breaking.
And of course, there's power. You can't just strap a clunky battery pack to this stuff. The solutions here are just as elegant as the devices themselves. A lot of them use wireless charging, just like your smartphone. Others have these amazing, stretchable, super thin power sources built right in. And then there's the most futuristic approach, actually harvesting energy directly from your body's own movements.
Okay, so we've got the materials, we've got the engineering, but, what's the point? What is all this incredible technology actually for?
Well, the end game here, the ultimate goal, is to achieve something called mechanical symbiosis. And it's a really beautiful idea. The whole aim is to create tech that is so perfectly matched to our biology, so soft, so comfortable, so safe, that our body literally doesn't even realize it's there. It's about a truly seamless integration of human and machine.
And look, this isn't just some far-off theory. This stuff is already being used. On the skin, you have these things that look like electronic tattoos that can monitor your heart rate or even analyze your sweat in real time.
And inside the body, scientists are developing soft implants that can talk directly to the brain to help treat complex diseases like epilepsy.
So it all sounds amazing, right? Like the perfect future of medicine. But achieving that perfect symbiosis, yeah, it's a lot harder than it looks. Even when you solve that whole mechanical problem, there's still one massive challenge left. And that challenge is called biocompatibility. See, just because something is soft and flexible doesn't automatically mean your body is going to accept it. Biocompatibility is all about the chemical and the biological interaction. Is this material toxic? Will it break down into something harmful over time? You just can't ignore the chemistry. And this quote from our source material really drives that home. Even a so-called wonder material like graphene, with all its amazing properties, comes with some serious question marks. Some studies are raising red flags about its long-term safety, which just proves that solving that mechanical mismatch, well, that's only half the battle. Which brings us to our final big question for today. Scientists all over the world are working like crazy to solve these final challenges, pushing us closer and closer to that goal of perfect, seamless integration. And it really makes you wonder, if our tech truly becomes biologically invisible, what's next?